I don't think I can tell if the stream is going.
Yeah, I'll let you know when it's up. It's okay. Our YouTube live stream is up, and I'm going to also record this. All right, Michael.
Oh yeah, feel free to jump in, Aaron, if I miss anything. Welcome everyone to Dynamic Walking 2020. Obviously, we're in a slightly different situation than we originally planned. So just to walk people through our original thought process, right? As we were looking at venues, and we had thought about the Jersey Shore for a while, and we checked out some places there, and looked around Pennsylvania and settled on a nice spot in the scenic Pocono Mountains. This is sometime late last year. It turns out that the venue we'd originally picked had some problems. They decided they were going to renovate the entire place, and so they ended up canceling our contract right before we signed it. And then, of course, a week after they canceled on us, this happened. And so two sort of disasters striking as far as our venue goes. I think they'll be okay, fingers crossed, rebuilding, but this was Pocono Manor in the Poconos that burned down.
Let me add, that is not photoshopped. That is actually what happened to our first venue.
Yes, this actually happened to our first venue. And then so we went back and started looking around again and found a different venue. This is the one that you probably saw on the website. A family resort out in the Poconos. It was going to be beautiful. They're, sort of like Camp Michigan, right? But upgraded to real beds and hopefully no bed bugs was at least the plan. And obviously that's not where we are today. Where we are today looks probably something more like this. And we're going to make the best of it here. We have a totally packed program today, so trying to compress what would normally be 4 days into one. So let's get to it. So this is our rough outline for the day. These are all East Coast times. You've seen these on the website. Just as a reminder, we're basically going to alternate back and forth between talks from the submitted abstracts. We have a couple invited speakers as well, and poster sessions / breaks. And the talks, right, are all going to be here on Zoom or on YouTube, depending on how you're viewing this. And then for the poster sessions and the breaks, we'll be going off to the spatial chat rooms that hopefully you've seen on the program. Okay. And then we'll wrap up the day with a little bit of a social hour. Again, time to chat. So we're trying as best we can really to replicate the in-person high level of interaction that we typically get at Dynamic Walking. So we're not just staring at a Zoom talk all day long. Okay. Just some quick logistics, right? If you want to ask a question during the talks, we're recommending you use the raise hand tool, and we'll be trying to monitor that as best as we can. If you need to, feel free to unmute yourself and jump in and just start chatting. Again, we're going for high level interaction. During the talks, make sure you're muted yourself. The Zoom room is going to go up to 500 people. We're almost halfway there now, so we'll see if we end up filling up. There's always the YouTube live stream for overflow. If you are in Zoom and you're sort of thinking, I'm going to be half paying attention, I'm not really going to be interacting, maybe YouTube is the right choice, just so you don't take that slot. And then for speakers, right, if you are planning on using videos, if you haven't done a lot of Zoom yet, there is a checkbox to optimize your screen share for a video clip. It'll downgrade your slide text a little bit, but make the video come through with a higher frame rate, so people aren't watching a slideshow. Okay, so the breaks are sort of the interesting thing here, right? We found this tool called Spatial Chat. Hopefully you guys have spent some time playing around with it, particularly for people presenting posters. We have 10 rooms right now. Hopefully that should be enough. Each room goes up to 50 people. Rooms 1 through 8 are for the posters. This should all be on the program. Room 9 is for the speakers from the previous speaking presentation slot. If you want to ask them questions or just chat with the speakers. And then room 10 is just totally unstructured. The abstracts, and posters, things that people have provided to us are all online, whether that's a PDF or a YouTube link or PowerPoint, anything that they sent us, we put up online as best we could. So you can go on, check out the abstracts and see them in full detail. And then during the poster session, right, go into the spatial rooms, chat with the poster presenter, get the full information. Feel free to sort of drift from conversation to conversation or room to room over in those spatial chats. Also, there is the Slack room, which I think a lot of people have joined as well. Feel free to jump in there and chat. Ask the poster presenters questions, or just organize discussions somewhere else. Okay. All right. Just sort of some quick, tips for using using special chat. If you're using Chrome at least, and you try to join special chat at the same time, it's going to fight for your camera. So either turn your camera off Zoom, or just sign out of Zoom. Click on the link, type in your name, and go from there. Right? You can be in multiple rooms simultaneously, so that is possible. Just be a little bit careful about which ones are showing, muting yourself in different rooms and showing your camera, etc. Once you're inside, some, again, quick tips. You can see who else is there, right? There's a little participant list. You can also just click on their name and you'll teleport yourself to wherever they are. You can share videos, images, or your screen, particularly for the poster presenters, and you can drag yourself around using your mouse. And you only hear people who are near you. So this way, each room can support lots of simultaneous conversations. It can support a more natural, movement through the room. You can also zoom in and out, right, using your mouse wheel. If you want to view posters, right, so the poster presenters are going to put stuff up in these rooms. The resolution there is sort of limited. So if you want the high-res version, you might want to right-click on the image and open it in a new tab. You might want to go onto the program and open up the details from there if you want the full version. Some people, I'm using one of Patrick's images here, because some people have gotten really clever with how they're designing their spatial chat rooms. So this is a screenshot from yesterday where Patrick was playing around. He has a poster here. He has a YouTube video sort of stuck on top of the poster. For the poster presenters out there, I think, be clever. Try to create this room as, leverage the fact that we're not just putting up posters onto a wall right now. You could be a little bit more creative than that. And that's it. So we'll get on to the program today. Happy to sort of pause briefly if people have questions. Otherwise, we're excited to get into the technical details. Thank you all for coming. Anything to add, Aaron? Are we good?
I think we're good. I saw a couple comments about the YouTube stream not working. I think it's up now, but if anyone has trouble getting to the YouTube stream, let me know. I see 137 people watching on that, so welcome to everyone on YouTube as well.
All right.
And I think Art is here to host the first session.
Yes, I'm here. Why don't we get started then? Okay, I'm Art Kuo, coming to you from University of Calgary, and I'm happy to chair the first session. And our first speaker is Friedl de Groote from Catholic University Leuven, and she'll be speaking on fast and physiologically realistic simulations to study neuromechanics of human locomotion. Friedl, you have 10 minutes.
Okay.
Plus 10 for answers.
Okay. I'm sharing my screen. I hope you can see that. Okay, thank you for inviting me. This is my first virtual conference. I hope all goes well. But just in case, I also put a link to the videos that I will be showing during my talk on the website in the program. So I aim at simulating human movement based on neuromusculoskeletal models without relying on experimental data. And such simulations can be used to enhance our understanding of the interaction between motor control and musculoskeletal dynamics. And I'm especially interested in using detailed models, as my ultimate goal is to use simulations to design optimal treatments for neuromusculoskeletal disorders. And such treatments often target specific musculoskeletal structures that therefore should be described in the model. However, model-based prediction of movement is challenging due to the high computational cost of numerical methods that account for the complexity of the musculoskeletal system. Although reductions in computational time were high over the last 2 decades, a recent study still reported 13 to 17 CPU hours for a 3D model with 25 degrees of freedom and 18 muscles. Our simulations were based on a model with 29 degrees of freedom. Each leg has 6 degrees of freedom, 3 at the hip, 1 at the knee, and 2 at the ankle. The lower limbs are driven by 92 hill-type muscles, and the upper limbs are torque-driven. Contact was modeled by a smooth Hunt-Crossley model. We simulated movement by minimizing a cost subject to constraints imposed by muscle and skeleton dynamics. We imposed the forward speed and either symmetry or periodicity of the movement. And we improved computational efficiency by combining direct collocation, implicit dynamics, and algorithmic differentiation. We enabled the use of algorithmic differentiation in OpenSim, and we developed an interface between OpenSim and Kazanski, which is an open source tool for algorithmic differentiation. And optimization problems were solved using IPOpt. When we assume symmetry, we only have to solve for half the gate cycle, which takes on average 35 CPU minutes on a laptop. The low computation time allowed us to explore the effect of the performance criterion on the predicted kinematics. And we found a human-like gait pattern when minimizing a weighted sum of metabolic energy rate, muscle activity, joint accelerations, passive torques, all terms squared per distance traveled. And here you see the resulting gait pattern. All terms in the cost function were important. So when we omitted or did not square metabolic energy rate, in yellow and blue here, we obtained a movement with large trunk sway. And when we removed the muscle activity term, in red here, the model adopted a narrow step width and activity of some muscles was close to maximal. Here you see a detailed comparison between the simulated walking pattern in orange and experimental data in gray. No worries if you cannot absorb all details. What I want you to get is that in general, simulated and experimental data are in good agreement. But there are some important differences that I will point out for you. We failed to predict knee flexion during mid-stance. Our model requires less extension torque than human subjects and hence less fasty activity. And in addition, we fail to predict ankle plantar flexion during push-off, although the simulated torque is in agreement with experimental data. And we were unable to improve these results by altering the cost function. We tried many things, including minimizing impact. Alternatively, it has been suggested that knee flexion during stance is important for stability, but this is not easy to implement. Hence, we were stuck until someday in January, my quads were so sore due to trail running without proper preparation that I spontaneously started walking like our model. And I realized I did not push off on my toes. And so we decided to give our model toes, and this solved our issues with the absence of knee flexion and knee extension torque during mid-stance. It gave us also some nice fasty activity. So the take home from this is toes are important. To gain confidence in our simulations, we explored the effect of varying gait speed, muscle strength, and prosthetic use on the simulated gait without changing the cost function. And in all those cases, we predicted realistic movements. And so here I will only discuss briefly the results from altering gait speed. So when we altered gait speed, the model predicted a continuum of walking and running gaits. Left, you see the simulated cost of transport as a function of gait speed, and each dot represents a simulation at a different speed. We predict a U-shaped relation between cost of transport and speed for walking in agreement with literature. Right, you see that we also predict a linear increase of step frequency with speed, also in agreement with literature. So we aim at applying our framework to improve treatment selection for neurological disorders. And I will briefly introduce a case study in a boy with cerebral palsy that we performed as a first step towards this aim. This boy walked in crouch, characterized by excessive knee and hip flexion during stance. And we had data from the clinical exam and MRI images, which allowed us to create a personalized model. We then performed a series of simulations to explore how each of the impairments of this boy contributed to the crouch gait pattern. First, we only accounted for bony deformities. As you can see in orange, bony deformities alone did not cause crouch gait. Next, we also modeled altered muscle tendon properties. As you can see in green, this caused our model to adopt the crouch gait pattern. Additionally, but not shown here, we modeled spasticity and a lack of selective muscle control, but these deficits did not cause our model to go in crouch. Hence, we think that muscle and not motor impairments cause crouch gait in this kid. And in agreement with our analysis, orthopedic surgery was successful in treating the crouch gait pattern of this patient. So far, we have been simulating gait with optimal open loop control, rather than by modeling control policies. And as a consequence, our simulations are not robust against external perturbations or sensory motor noise. And as a first step towards better motor control models for walking, we studied sensory motor transformations in perturbed walking. If walking is perturbed, for example, by a push to the pelvis, people use two strategies to restore balance. They use an ankle strategy to shift the center of pressure under the stance foot and/or adapt step length. We studied sensory motor transformations underlying the ankle strategy. And we found that delayed feedback from center of mass, position, and velocity explains variations in ankle torque in response to perturbations. Here you see ankle torque as a function of center of mass position, center of mass velocity, and then you also see the correspondence between the measured ankle torque and the reconstructed torque from feedback from position and velocity. And when we implement center of mass feedback in the reflex model of Bear and Her, its ability to predict the measured joint moment in perturbed walking drastically improved. Please go visit Maarten's poster for more details. We also want to capture how uncertainties shape human movement in our simulations. And therefore, we are extending our optimal control framework to a robust optimal control framework. And to compute robust optimal controls, we extended the state with the state covariance matrix, describing the uncertainty on the states due to noise. We describe the dynamics of the state covariance matrix by the continuous Lyapunov equations, and this allows us to penalize state uncertainty in the cost function. We solve the resulting problems using the tools I discussed before. Here you see an example for a simple torque-driven walking model with 5 degrees of freedom. As you see, optimal open loop controls are not robust against Gaussian motor noise. Therefore, we added full state time varying feedback to the model, and we extended the cost function by a term minimizing the variance on the state trajectories. The resulting simulated movements are robust against motor noise. So now we can start investigating to what extent robust optimal control explains observed behaviors. When we applied external perturbations to the model, we found a correlation between the ankle torque response and the center of mass position and velocity, qualitatively similar to what I just showed you in the experimental data. And this is interesting since we did not specify the control structure. The model is controlled by full state feedback. So we are testing the robust optimal control framework against a range of observed behaviors that are well documented. And if you want to hear more, you can go visit Tom's poster. And with this, I want to acknowledge Antoine Fallis, Tom van Wouwen, and Maarten Afschrift, who did most of the work that I presented here, as well as my collaborators on these projects and my funding. Thank you.
Thank you, Friedl. If people have any questions, please raise your hand in the chat and or I guess in the participants list, we can see if you raised your hand. Maybe I'll start with the question. Friedl, you did pretty well with your metabolic cost minimization, and I'm wondering if there was any difference in what you were using for your cost function versus what other people have used. If you remember, Anne Colewine showed that when they minimize what sounds like a similar cost function, that the model didn't do such a great job, say, on predicting the cost for going uphill or downhill.
I don't think we do very good, so we found that different models predict very different costs, but they do predict similar walking patterns. So it seems that the cost, like the metabolic energy model that we use in the cost function, does not have a big influence on the simulated gait pattern, but has mainly a big influence on the simulated cost of transport. And I think I can quickly show this here. So here you see simulated movements that were predicted by different cost function, by different metabolic energy models. There is some variation in the cost. There is also some variation in like the joint angles we predict, but it was not very different.
I see. Okay, we have a question from Elijah Kuska.
Dr. de Groote, thank you for that talk. It was a fantastic talk. I just had a quick question. So you pointed out that you had some discrepancies in the plantar flexion moment and knee extension moment. And then when you were using this model for CP gait, that gait you were matching was one that had decreased plantar flexion moment and decreased knee extension moment. So I'm wondering if the improvement you saw from that patient-specific model was maybe from that discrepancy in modeling this population that already has these issues. And I'm wondering if you would see something different if you modeled someone with like a stiff knee gait and an equinus where there's increased knee extension and increased plantar flexion moment.
Okay, so well, just clarifying, we predicted the plantar flexion moment all right. It was mainly the knee extension moment, and yes, I do agree that that might have influenced that the lack of toes, because there were also no toes in the simulation for CP, might have influenced the results, and that there might be a bias towards indeed where patients use this knee extension torque or not. And I cannot really tell you how our results would look different. I can only say that that we used that we varied parameters and that we could see what their effect was. But you're right, there might be a problem still.
Thank you.
Next, we have Matt Hanford has a question.
This one might be along the same vein, but when you were looking at that knee flexion torque at heel strike, it wasn't appearing in your optimization, which we see pretty often. But then when you added in the toes, it appears. Do you have a sense for why the addition of toes would create that knee flexion torque?
Yeah, it's a very good question, and the reasoning was completely inverse because I was trying to avoid my sore quads, that I felt I wasn't pushing off on my toes, and then I looked into literature to data from like gait analysis data from a person with amputated toes, and it looked kind of like our models, so that convinced me even more that the toes. So basically what I think is because your foot, you can kind of bend it, you increase your leg length towards the end of stance, and then you get this different motion. I don't know whether that completely answers your question, because the intuition was actually the other way around. It was like, oh, if I don't use this muscle, I never push off from my toes.
It's very fascinating because this is something that I've seen repeatedly in my own simulations where this exists in reality, but anytime I try to do it in a simulation, I don't see the same
Yeah, so I
flexion
totally
torque.
relate to that because we've been trying for months to get it in our simulations, and we published the study without having it.
It's very fascinating.
Okay.
Thank you.
Thank you.
Let's take a question from Andy Ruina.
Maybe you said this. I had trouble understanding some of your words, and maybe Art's question addressed this also. But my recollection is that those of you who are doing this realistic optimizations, at least a year ago, everybody was getting the overall coordinations kind of okay, and you're doing really well at that. But they were getting the overall energy cost way wrong. And in your graphs, it looked like you weren't getting the energy costs way wrong. Is that because you put a fudge factor in, or has the situation changed since last year, or do I misunderstand something?
No, but what we see is that depending on the model we use, the absolute cost is very different. So I wouldn't say we get the absolute cost very right. It's more that I think we get what we get right is how the cost changes with gait speed.
But you showed a graph of your walking and running. That I think that's what both Andy and I are referring to.
That's the Perturbations model that we used here. And we didn't do any tweaks to it.
So you're saying that you get, without cheating, you get the right energy cost for walking and running.
Yeah.
And that seems to me quite different from what everybody was saying a year ago at this competition at the World Congress.
Yeah, so the only thing I can say to that is so actually maybe you don't expect it to be that right, because we are missing the vesti activity, as I showed you, because this was a model without toes. And also our experience is that if we do inverse simulations, we don't get it quite right. And also it's very variable across models. Yeah.
Can you just say what the key difference is, what you have to get right? I just couldn't hear the words very well.
What the key differences are?
You say what does it take to get the absolute energy cost correct? Say for this graph that you're showing now.
So what we did, we used the model by Perturbations, and we did not do any tweaks to it. But what I'm mentioning is that if you would do like an inverse analysis where you have the knee extension moment, we didn't have it here because it was a model without toes. So you would kind of expect us to underestimate the cost, which we did not.
Okay, I think Chris Atkinson, do you have a quick question? And meanwhile, let's ask the next speaker to come to the front and set up their computer.
I'm interested in whether muscle properties matter and whether you tried to figure out sensitivity of various parameters in these models to your results. Do you have any idea which parameters in the model matter?
We only just started to look at sensitivity, but model properties matter. For example, if we increase maximal contraction speed of the muscles, our walk to run transition speed is lower. So we transition faster. And then also in the child with CP, we really see that, yeah, if you get contractures in the muscle, so short optimal fiber lengths, the gait pattern is totally off, but we are in the process of doing this exercise like more systematically.
Okay,
Great,
thank
thanks.
you. I think we're going to have to move on. Our next speaker is Zhao from Georgia Tech, speaking on robust task and motion planning for agile locomotion in the now.
All right. Good morning, everyone. So thanks for the intro, Art, and I also want to thank the dynamic walking community inviting me for this talk. So today I'm going to talk about some of our recent work on high-level symbolic planning for agile locomotion in complex environments, and how to reason about the safety and the robustness. I do want to say this work provides a different way to solve contact sequence planning problem from the high-level perspective. So to start, I would like to motivate a little bit of our work using this one of the oldest extreme sport in Netherlands, which is called Fair Japan. I hope I pronounced it correctly. So in this sport, each athlete is given a long pole, and they need to use this long pole to swing its body over the water and land on the sandbed on the other side. If we treat this whole motion as a motion planning problem and decompose it into multiple different phases, you can see this motion is composed of a sprint to the pole, jumping, grasping, and climbing to the top of this pole, while at the same time maintaining the body moving forward properly. And here we can see how to plan the motions during each phase and when to switch to the next phase are all critical for a successful run. And this is definitely a highly dynamic locomotion problem involving interactive dynamics and the sequential task composition. This scenario motivates us to question whether robots can achieve such level of agile behaviors and how to make contact decisions properly. And deviating from bipedal locomotion, in this study, we have a large focus on generalizing the locomotion behaviors to multi-contact scenario using all limb contact. And this locomotion scenario in constrained environments do have real-world merits and applications, such as the Thailand cave rescue and the ongoing DARPA subterranean challenge. From a high-level perspective, a fundamental question we are interested in is what type of decision-making and planning algorithm do robots need to achieve very agile, robust, and reactive behaviors through contact. And as we all know, I think contact problems have been widely explored this year, and multiple lines of research have emerged, such as like trajectory optimization, solving contact sequence, and people use simplified locomotion models to plan for the locations, multi-contact planning from humanoid community, and the more recent work like learning contact model, soft contact model, involving either numerical or physical softness, and a lot of bio-inspired works from animals and humans. However, I do want to say, I think among all of these works, we still means a general planning framework that can address a variety of environmental events and make the robots respond to these events properly. We have been working on this direction for the past few years and taking a completely different route. As presented in the previous dynamic walking, we have a large focus on reactive task planner synthesis by formulating this whole body locomotion planning problem as a two-player game. So the goal here is synthesize a winning strategy such that the robot can always win the game, and which basically means the robot can successfully maneuver this constraint environment. To achieve this goal, we employ a temporal logic-based motion planning approach to synthesize correct by construction winning strategy, which is represented by the automata. And here I show a fragment of this automata on the right. As we can see here, this automata incorporates a set of discrete states, including the environmental event states, robot keyframe states, contact configuration, and the locomotion mode. And I do want to comment out our two-player game is executed in a turn-based pattern. So the robot task planner responds to the environmental events within only one walking step. So that's why we call our method as planning in the now. As to the task specification, we get a lot of inspirations from real human locomotions, especially those seen in the parkour and the gymnastics. So we extract the essential locomotion dynamics, make the model abstraction. And in our study, we take into account a variety of simplified locomotion models, such as inverted pendulum model, pendulum multi-contact hopping, or even rimless model. And when the robot sense environmental states, it's going to make a decision on the sequential composition of this template model and generates the motion decision graph through the two-player game. And here are some results on integrating the high-level task planner with the underlying phase-space motion planning. And here we can see this robot can dynamically maneuver in this constraint environments using a variety of contact decisions. And even when some emergency events happens, the robot can, like, for example, the train get crashed, the robot can grasp the ceiling wall, or maybe a human appears in the scene, the robot is going to come to a stop and wait until the human disappear again. And we also generalize this locomotion behaviors to more complex situation. For example, if both terrain and the ceiling wall get crashed, the robot is going to initiate a leaping motion, or if the terrain gets a narrow passage, it's going to use a sliding motion through this complex terrain. So here, the locomotion phase-space trajectories in the robot center of mass space are sequentially composed through the symbolic decisions. And as I mentioned, the correctness of this sequential composition is guaranteed through this reactive task planner. But the problem is it's only guaranteed at the discrete level, at the symbolic level. So when we have low-level model uncertainties like terrain disturbance or external perturbations, this formal correctness guarantee is going to be broken easily, and it can cause failure at the low-level execution. So now the problem becomes how we can design or reason about the robustness at the discrete level and design corresponding robust planning strategy. So to address this, we propose a robust margin design using analytical solutions of our locomotion manifold. And as we all know, this locomotion manifold have this valley type trajectory profiles. And we derive analytical tangent cotangent manifold solutions thanks to the nice property of our locomotion models. And this manifold is used to design a non-Euclidean state space discretization. And this is a more advanced approach than just a traditional naive grid word discretization, and make our abstraction more consistent with the underlying locomotion dynamics. So based on this discretization, we propose a set of robust margins around this nominal keyframe state. And given this robust margin design, we have a systematic procedure to compute feasible robust keyframe transitions through the reachability analysis. And here are the steps. So first, we assume there is a nominal keyframe transition pair solved by the high-level symbolic planner for 2 consecutive walking steps, and the green cell represents this the nominal keyframe state. And then we are going to expand this nominal cell by using an epsilon radius and take the neighborhood cells into account as alternative keyframe transition pairs. And then through the reachability analysis, we can solve all the feasible robust keyframe transitions in this scenario. And here we can see when we have local state perturbations, these robust keyframe transitions allow a successful run by selecting alternative key transition possibilities. And so this is the pretty robust approach we propose to solve handle uncertainties at the low level. But there's one more problem. So sometimes the disturbance could be very large, and it can perturb the states out of this robust margin. And in this case, this keyframe transition approach will not work. So in our planner, we have another replanning mechanism to search for different locomotion modes and design corresponding keyframe states. So for example, in this scenario, the robot is going to initiate a hopping motion, but it's going to land for the next step, but it just realized that the next step also become crashed, and then it send a new command to the high-level task planner and ask for a new command. So basically grasp the ceiling wall and to achieve the successful run in this case. So at the last, I just want to maybe briefly mention an ongoing direction in our lab about summation and the task planning of heterogeneous robot teaming and the navigation. So in particular, we are highly interested in collaborative behaviors involving locomotion, manipulation, like aerial robots, and how to unify terrestrial and aerial coordination. And I want to say this problem is fundamentally more challenging than just the 2D mobile robot navigation due to the complexity of the locomotion dynamics. For example, when the robot makes a turn, we need to take into account the constraint from the underlying locomotion dynamics and incorporate them into the high-level task specification design. And here we propose a hierarchical framework for navigation in partially observable environment and reasoning about the safety from different perspectives. So as a takeaway message, for multi-context Agile, like the locomotion problem, there are great opportunities to export and leverage symbolic approach and like a temporal logic and AI planning method. And I think they can help us to explore the discrete structure of our planning and optimization problems. As to robustness, I do want to say it's very helpful for us to reason about uncertainties not only from the discrete, not only from the continuous level, but also the discrete decision level, and how to design robust discrete transitions and robust margins. And if you're interested in hybrid locomotion planning, we do want to emphasize the importance of unifying a variety of locomotion models and make the robots react to diverse environmental events. So with that, I'm going to stop. Thank you.
Okay, thank you. Do we have any questions? We have Chris Atkinson.
So there's a paradigm shift going on in motion planning, robot motion planning, away from methods that just find feasible trajectories to methods that optimize something. And this is also a huge issue in understanding biological motion. When is it, can we sort of, as in the last talk, predict motion based on optimization versus, you know, some transient motion that we cooked up on the fly and it's hard to describe with optimization. It seems to me this approach is all about finding feasible motions, which, you know, is in some sense old-fashioned AI, and there's no element of optimization in it.
Right. So yeah, thanks, Chris. Yes, I think that's true and not. And so in this framework, yes. So when we design the locomotion behaviors, so we mainly use the simplified models, and in this work there's no optimization involved. But in another work, we do like kind of solve optimization problems and take into account a variety of like physical constraints and cost functions to reason about what is the optimal solutions. And I didn't present in this talk, but let me see, maybe I have something I can comment a little bit more. Yeah, so this is some slides I didn't mention, but literally we can solve like a kind of whole body optimization, incorporating multiple different constraints like contact constraints, centroidal dynamics, whole body dynamics. But our whole idea is basically solve this problem in a kind of distributed way. And the block on the upper right, you can see this is the centroidal dynamics, and actually the AI planning approach I just presented can be incorporated here. And so for example, we have a set of simplified models, and at the same time taking into account all other different kind of dynamics constraints, and get kind of the optimal solution. But yes, in our current planning framework, we haven't incorporated this optimization problem yet. So it's definitely, I think, computationally it's going to be quite heavy.
So that another paradigm issue though is, do you do this symbolic reasoning first and then search in a graph of options and sort of locally optimize each path through the graph? Or do you just use soft constraints and explore infeasible motions and essentially use gradient descent to get you to something that's feasible and optimal. So one way to phrase it is, should you do hard constraints or soft constraints?
Okay, I mean, I'm trying to understand the context a little bit more, like the soft constraint, hard constraint you are talking about in terms of the optimization framework.
Yes, one way
Oh,
to do
different.
Soft constraints is, for example, every possible contact point is contacting every possible part of the environment all the time. And you gradually figure out what it's actually going to contact by having weights that go up and down. One version of this is contact invariant optimization by Igor Mordach.
Yeah, yeah. I think the contact implicit treasure of the kind of community have explored a lot on this, like how to relax the constraints, like numerically, to make the algorithm more computationally efficient. But I do want to comment that in this work we didn't solve problem from this way, and so what we do is basically we discretize the environment, and for example, in our situation, we take into account like a discrete set of stair height and the emergency events, and there are like a discrete robot action states and the locomotion mode. So I want to say it's completely in the discrete reasoning domain, and not solving through the optimization method. Does that kind of answer your question? All right, thanks.
Okay, but why don't we move on? I think we have a question from Jonathan Hurst.
Yeah, maybe this is an easy one, but what is your action space, or what are you commanding? Are you commanding positions? Are you commanding torques? Are you commanding, PD gains or compliances or impedance control?
Yeah, so this is a completely high-level task and motion planning, and we haven't touched anything on the low-level control. I mean, which is definitely very important. But we do have like models in our like a task planning. So we basically use the simplified models, and there are control actions, which are basically your foot locations and your torso torque, but it's kind of the control action of your reduced order model.
Do you know then that a feasible robot could follow any of these trajectories, or how would it interact with an environment when it makes a contact when perception is noisy, late, and wrong?
Yeah, so again, I want to highlight I think there are a lot of like low-level uncertainties or disturbance or even perception inaccuracy, but our approach is basically abstract all of these kind of uncertainties or disturbance in the robot center of my state. And if we can build up a mapping between these like detailed perturbations and uncertainties with the like center of mass state deviation, and then we can apply our high-level planning approach to address this uncertainty. So I do want to say the robustness is primarily reasoned in this high-level reduced order state space. Yep.
Understood.
Okay, I'm afraid we're going to have to end the discussion here and move on to the next one. Our next speaker is Jonas Rubenson from Penn State, and he's going to be talking about decoupling the metabolic and neuromuscular control of human walking.
All right, hello. Let's set up my... So everyone should see the PowerPoint, I hope. On the... All right, well, thanks for having me speak here today. It's my first dynamic walking meeting and also my first online meeting. So I'm gonna present work that was led by Kirsty McDonald when she was at Penn State, and who's now an assistant professor at the University of New South Wales in Sydney, Australia. So I think it's generally well accepted that humans, they often adopt gait patterns that minimize energy expenditure. So for example, humans, when they're permitted, will select energy minimizing speeds or stride frequencies and step widths. But what is, while these energy minimizing behaviors have been demonstrated, the actual underlying control targets during walking remain much less clear. So one possibility, of course, is that we are indeed sensing or perhaps somehow computing total energy cost and are adjusting our gait according to this information. But it's also possible that other control targets or even other optimality criteria are prioritized during walking, and that low energy is an emergent property. So for example, it's possible that the target of control is not whole body energy expenditure, but rather arises at the level of individual muscles. And there's some indirect evidence for this from simulation studies, where minimizing the sum of the activation squared of individual muscles results in more realistic simulations of both movement and energy costs. And in these simulations, it's important to keep in mind that high activations in any single muscles are what is being penalized. So, so that these have been shown in simulation studies, but there's really very little empirical evidence for this locomotor control scheme. So what we set out to do was to design an experiment that pits whole body energy cost versus individual muscle activations in a way that prevents the subject from simultaneously having a low total energy cost and a low muscle activation cost. And so the way that Kirsty McDonald designed this was to pit crouch walking against incline walking. So crouch walking, it has a relatively low energy cost, but it has a high activation cost because it places a disproportionately large burden on the quadriceps muscles. In contrast, incline walking has a high energy cost, but it maintains a relatively low activation cost because it maintains a more even distribution of muscle activations. So we tested this in 10 individuals. We used standard EMG and respirometry, and we compared the crouch walking to 4 incline levels. And our activation cost was formulated as the sum of the muscle activation squared from 7 major leg muscles. And I'll just show you, sort of demonstrate our experimental setup briefly. So the subject, when they break this virtual ceiling, the treadmill begins to incline. And if they then crouch below the virtual ceiling, the treadmill returns to a level position. And the subject was asked to explore these conditions and then select the one that they preferred and continue to walk in that condition for another 5 minutes. So when we asked people to choose between crouch walking and level walking, we found that both whole body metabolic cost in the blue bars and the activation costs in the orange bars here were lower during level walking, perhaps not surprisingly. So there's no reason here to expect that people would select crouch walking. And in fact, they did not. So all participants faced with this decision, they select level walking. However, what happens when we ask people to choose between crouching and steeper inclines? So at 12 and 18% inclines, we successfully dissociated whole body energy cost and muscle activation costs. So here we see that energy cost is low in crouch, whereas activation costs are low during the incline condition. So the result here is an activation penalty for selecting crouch and an energetic penalty for selecting the incline. And so now when people are faced with this dilemma, what do they prefer to do? Turns out 9 out of 10 participants selected the incline condition. So here they're opting to penalize rather than minimize energy expenditure. Okay, so what happens if we raise the incline further? So at 18 or 24% grade, we observed that there's only an energetic advantage in the crouch condition with no difference in activation costs. So in this case, why would you not select to move more economically when there's no disadvantage for you doing so. And this is exactly what our subjects chose to do. So I think I'm almost at time here, or over time. So in conclusion, what we've demonstrated empirically is that is an example of where muscle activation is prioritized over energy expenditure. So energy minimization only occurs when there is no disadvantage to high activations in individual muscles. And I'll leave us with one question, and that is walking optimized for effort in individual muscles? So I'll leave it there. Thanks, and happy to take questions.
Thank you, Jonas. Do we have any questions? Well, Jonas, I like the design of the experiment, but I do have one concern, which is I feel like in these experiments, if I just make the subject miserable, I can get them to choose different behaviors. So like, you know, I could scratch my fingernails on a chalkboard when they're in one condition, and then they might avoid that. But is that indicating what people really prefer during normal locomotion?
Yeah, so I think what you're maybe inferring is that it could be uncomfortable. Like crouching could just be uncomfortable or painful, and therefore they want to avoid that condition. Yes,
and there are all sorts of discomfort that we avoid if they are presented to us, but they may not be representative of what we are, you know, usually waiting.
Yeah. Yes, I mean it's certainly a factor. It is uncomfortable to walk crouched. I think one of the compelling aspects of the data is that we see this. We see the activations when we go to the steepest incline. You know, we see that now when there's no longer an activation disadvantage or penalty, then you see people revert back to the and now they choose the energetically minimizing gait. And so that I think is a bit of data that I think seems to suggest that it could be something in the activations. Because that would not necessarily have been predicted if it was just uncomfortable or painful. So there's some data that I think supports activation, but you're right. I mean, we can't disregard other aspects, like it could be painful, and people are avoiding a painful gait.
But also, you're really talking about the context of this just walking on the treadmill, and there's lots of evidence that, you know, if you block out an ankle joint, that people continue to activate their ankle muscle. So, you know, you can't really argue that walking as a whole is optimized based on individual muscle activation.
Yeah, right. And that's sort of, I posed the question at the end there to sort of spark some discussion and debate about it. I don't know. I mean, I don't think, I'm not suggesting that necessarily that we're showing that we're definitely optimizing for effort in individual muscles. It might also be that we're you know, that the activations are somehow mapping to energy as well, and that, you know, we could be sort of tricking the brain a little bit, thinking that it's energetically costly. Yeah.
Andy, do you have a question?
Yes, just on the very last thing you said. I missed like your definition of energy. So when you talk about effort and activation and energy, and you're trying to factor them, it sort of matters how you define them. And so, like, I think everybody would agree, for the most part, people do things which more or less minimize some kind of effort, and then trying to tease out what effort is versus energy. It sort of matters how you define energy. And I missed that definition.
So energy is calculated from it's metabolic energy. So that is in joules. We reported it as cost of transport, but we could have had it as a rate of energy expenditure because everyone walked at the same speed. So the energy is metabolic energy. expenditure. And the activations are the sum of the activations squared from the individual muscles. And we normalize them to level walking. We have to normalize them somewhere. I didn't mention that, but.
So these are both costs per time.
They are both, yeah, so the numbers in this on the figures are actually costs per distance, but it would be the same, because we're walking at the same speed, they wouldn't be different if we express them as a cost per time. Yeah. Okay,
Jerry?
So to what extent do you think there might have something to do with willpower also? Because you know, it might just require, for some of these motions where you have to actually try hard to make it happen, whereas something that's just taking a lot of energetic costs might not be that hard. Like where you can do it without really thinking about it. You don't need to exert yourself mentally.
Yeah, that's a good question. You know, there could be a bit of a cognitive cost with having to look at the virtual ceiling and stay below it. And we did consider, you know, is that a factor? Because there is not the same sort of cognitive load that might affect people's willpower. I think that's what you're getting at when they select the level walking. Now they don't have to, they can kind of relax in a sense, having, you know, in terms of the experimental focus that they have to.
And also, besides just having to think about that, you need to go under the barrier. Just like when you try to sprint, you actually have to put effort into it, right?
Yeah.
You have to be using your brain to overcome what everything just normally wants to do. Whereas walking, you can, proverbially walk and chew gum at the same time.
Yeah. Yeah, I think that is a factor here as well. Yeah.
Okay, thank you, Jonas. Let's move on to our next speaker. Next, we have Robin Riethmüller from University of Stuttgart. And the title of the talk is Learning Optimal Gaits on the Quadrupedal Robot RAMbi. Robin, I'm not sure if we can hear you.
Do you hear me now?
Yes, we can. Please go ahead.
Perfect. So thanks for the introduction. If we think about legged robots and the possibilities that we as engineers have to create and generate motion for these systems, I want to highlight a powerful technique called optimal control. And people in our lab in Michigan and now in Stuttgart, we have a long history of using optimization to create gaits. Here, for example, you can see gaits we found during an optimization for a conceptual model of a quadrupedal robot. But we use the same methods for a realistic version of a real bipedal robot. The found gaits can be seen down here. So the question that I have now is, how do these results translate to hardware? Because as we all know, no matter how precise our model is, it's just an approximation of the real world. So if you wanted to truly find the optimal gaits, we need to directly optimize on hardware. When optimizing on hardware, there are different approaches that can be taken. So firstly, you can try to do trajectory optimization. Another approach would be trying to learn a control policy, which maps the states of our robot to motor torques. However, in both of these cases, we are optimizing over functions. And during the learning process, there might be the possibility that unstable trajectories occur and the experiment will fail. So our approach is sort of the combination of those two, where we define a parameterized control policy, which is versatile to allow us walking at different gaits and walking stably over a large set of parameters. And then we optimize over the parameters. So there are two challenges that arise here. How do you define a controller that is versatile and enables walking over a large set of parameters and prevents failure during the experiment? And how to choose the parameterization. So in our case, we came up with the idea of using virtual model control as a tool to stabilize main body motion. and then define parameterized main body trajectories as well as swing foot trajectories in order to locomote RAMbi forward. And lastly, we just define the gait scheduling algorithm, which allows RAMbi to change its footfall pattern. So given our controller working, as you can see in this little video, we can now think about doing online optimization. And there are a lot of things that have to be implemented to allow optimization directly in hardware. And unfortunately, I do not have the time to go over all of these in detail. So I just want to highlight two of them. Firstly, the cost function that we use for our optimization is the cost of transport, where we measure the positive electrical work. And secondly, the optimization algorithm that we apply is the covariance matrix adaptation developed by Hansen. So now to the bad news. Due to Corona, we were only able to optimize over one parameter so far. And we were thinking hard about which parameter we choose as a candidate to optimize over, and came up with the swing height, because we believe that the swing height is something that highly depends on the interaction between the ground and the foot. If we think about different values for the swing height, several scenarios can appear. Too low values of the swing height will lead to scuffing. Too high values will lead to a higher distance we need to travel during the swing phase, and both will lead to an increased energy consumption. So given these two boundaries, there should be a value for the swing height, which minimizes our cost of transport. We tested our framework in simulation, and indeed we found an optimal. So the blue line is a parameter sweep, something we can do in simulation since we don't care about experiment time. And the red circles or red crosses are values tested from the optimization algorithm. Then we went ahead and did the same in hardware, where we can see a similar behavior. Lower values than the optimum lead to scuffing or sliding on the ground, and higher values of the swing height lead to an unnecessary distance travel, as I just explained previously. So by comparing the results from simulation and hardware, we can also see that if we would have applied our simulated optimal swing height directly to hardware, we would be in the scuffing region and potentially failing to walk. So even though we were only able to optimize over one parameter so far, these results nicely show the differences between our model and the real robot, and they show the necessity of optimizing directly on hardware. Thanks for your attention. Here's literature that I used throughout my talk. If you have any questions, feel free to ask now or later on Slack or the spatial chat.
Okay, thank you. We have a question from Kevin Green.
Hi, Robin. Thanks for the talk. First of all, I want to say I really like this approach. I think it really is a great way to look towards moving from sim to hardware. I guess my question comes down to because we're so restricted on the space of parameters we can actually adjust, why should the final parameters that we're actually tuning be human understandable? Shouldn't there be some, more useful representation that we can get at that more, makes the, the time on hardware more useful?
Yeah, I can say that other parameters might be more beneficial and leading to faster results in optimization. And we don't know yet which parameters are really expressive. But so for the parameterization we chose all the parameters to be somehow understandable for the human.
Makes sense. Thank you.
Steve Heim.
Hi, Robin. So I would think that you would still want to warm start your hardware optimization by doing at least some optimization in software. But what you pointed out is then you might actually start from something that actually fails completely. So would you optimize over some other kind of cost function in simulation to try and avoid this, or how would you approach that?
Well, first of all, we'll try to improve the simulation. Because if you look at it, there are a couple of differences in the cost of transport values and stuff going on. So I would firstly try to get a better simulation, and then, well, if you want to find an energy efficient gate, I would still stick to the cost of transport.
Okay, if there are no further questions, I'm not seeing any. Okay, thank you, Robin. Let's move to our next speaker.
Thanks for letting me talk.
Our next speaker is Meghan Kazanski, and she's from University of Texas at Austin, and the title of the talk is Stepping Regulation Adapts to Lateral Perturbations. Meghan, I'm not sure if you're speaking, but we don't hear you yet.
Can you hear me now?
Yes, we can.
Okay, great. Sorry about that. All right, let's try this again. All right, so thank you. Yeah, I mentioned that now we're at Penn State, but this work was done when we were at UT Austin. All right, so briefly, I do first want to mention that this work has recently been published. So if there are more details on anything that I discussed today that you'd like to see, you can go ahead and check out this publication. All right, so when we're walking, we're constantly being faced with different walking contexts and different task goals. So how do we modify our stepping amidst these changes? In particular, how do we do this in the frontal plane, where stepping is particularly relevant to balance and stability? So we looked at how people modify their stepping regulation laterally by presenting them with various balance challenges. We had young and older adults walk in 3 contexts. The first, no perturbations, just normal treadmill walking. The second, walking while we oscillated the treadmill platform laterally. And the third, they walked while we oscillated their virtual environment laterally. So in the consideration of regulation of lateral stepping, there are 3 candidate variables that emerge as potentially regulated. Lateral body position, ZB, this change in position, delta ZB, and step width, W. And as you can see from normal walking, it's not immediately obvious which of these are being regulated. They all vary and fluctuate from step to step. So to determine how humans regulate lateral stepping during normal walking, we recently used multi-objective control models to replicate the stepping dynamics that we see during normal walking. And we found that humans primarily regulate step width with some regulation of body position. The step-to-step regulation of this model is defined by this 2-state goal function here, the objective being to drive this function to 0 to minimize the parameter errors with respect to desired values. And you can see here from this state update equation that the state of each variable for each step is based on its state at the previous step. So optimally controlling ZB and W result in 2 different foot placements. So we use a weighted average representing a trade-off between the control of these variables to determine the final foot position at each step. And we use this model, we perform sets of simulations to try and identify the sources of the changes in stepping regulation that we see experimentally, or stepping dynamics that we see experimentally. So here are the experimental results. We have body position and step width, and we have plotted variability and statistical persistence. In short, a smaller statistical persistence represents a greater likelihood of correction of deviations in subsequent steps in the opposite direction. So why do we see these experimental changes going from the normal walking condition when we introduce visual and platform perturbations, we see these consistent increases in variability and decreases in statistical persistence. So why is this happening? It's possible that this is simply because of the perturbations themselves introducing more system noise. So to test this, what we did was we took the models that I just presented and we varied the additive noise term in these models. And as we increase the additive noise term, you can see that for ZB and W, the variability of these parameters increase. And this is what we saw experimentally, and this is what we expected. However, this increase in additive noise does not explain or replicate what we saw experimentally in terms of persistence. So there's something else going on here. So next, we considered that perhaps this change in persistence is attributed to people's shifting their proportion of W to ZB control. So modifying this trade-off. So to represent this in the models, we varied the control proportions. And we saw that particularly for statistical persistence, ZB and W trends move in opposite directions and they really don't replicate what we saw experimentally. So this is likely not the strategy that humans are using to adjust to these perturbations. So the third thing that we considered is that these changes in persistence are perhaps attributed to people's increasing their control over these parameters, perhaps simultaneously. So to represent this, we varied the overall gain terms in the models, and we saw that the statistical persistence trends decrease for ZB and W, and this corresponds and replicates the results that we saw experimentally. So this is one potential strategy that people use to respond to these perturbations. So as expected, these models confirm that stepping variability increases that we saw are largely driven by the perturbations themselves, even when these perturbations aren't physical. People did actively modify their stepping in response to these perturbations, not by modifying this control trade-off, but by increasing control of ZB and W simultaneously. The sources of these changes are important, they're context dependent, and they can't be discerned experimentally. So it's really important that we continue to implement these models to help us identify these sources. All right, thank you. I'll take any questions at this time, and here's some related works that we're presenting later today.
Okay, thank you, Megan.
Yes.
Questions like Jonathan Hurst.
Yeah, so I guess my question is maybe a little bit tangent. So in your observations, while you were doing these perturbations and you're observing people doing their side-to-side stability, I know in the past, like past dynamic walkings, Jerry Pratt talked about high-speed running and how foot placement, the coupling between the lateral position and the yaw is very much like a bicycle. You're trying to keep your feet under where you're going. For these slower speeds walking, did you see a coupling like that, or is it very much decoupled where people just step sideways independent of their yaw?
Yeah, so we consider the relationship between those things decoupled. So, or at least in terms of we consider the control of step width and lateral body position decoupled. Of course, if we're considering like the rate of change of body position, that of course is related, but we actually don't consider that in our model. So we found that heading wasn't something that was really being regulated.
Okay, thanks.
Yes.
Any other questions? I guess I have a quick one, which is you did detrended fluctuation analysis, and what's the intended meaning, so to speak, for that measure?
Sure. So I'll scroll back up to the plots. So for this, I didn't really have time to unpack it, but what we look at is, like I briefly mentioned, these decreases in this indicate decreased statistical persistence. So when you decrease the detrended fluctuation analysis exponent alpha, you're considering that a deviation at one step is more likely to be followed by a deviation in the opposite direction on the subsequent step. So we look at the time series, we sort of bin in different sized bins, look at the fluctuation. We look at the relationship between the fluctuation and the bin size. And then the slope of that is our alpha exponent. And so 0.5 is sort of considered optimal, or that deviations are equally likely to be followed by corrections in either direction. So we're really looking for values around that 0.5 mark for optimal correction.
Okay, thank you.
Sure.
Okay, if there are no further questions, why don't we move to the next presentation? Next, we have Ken Ingraham from University of Michigan, or at least I think she's still at University of Michigan. And her talk is user preference of applied torque characteristics for bilateral powered ankle exoskeletons.
Thanks, Art, and thank you to Aaron and Michael for organizing this virtual conference. This work is being done at the University of Michigan, but also advised by David Remy, who's at the University of Stuttgart, and Elliot Rouse at Michigan. One moment. There we go. So high performance exoskeleton systems, like the ones that are pictured here, really enable us to study how to control these devices in order to maximize the device performance and also the benefit to the user. And as a community, something that we talk a lot about and think a lot about is how to optimize exoskeleton controllers in order to achieve some desired impact on the user. Now, this process always starts with an objective. One example that we use often is reduce the metabolic cost of the user. And then optimizing a controller means finding the control parameters that best achieve this objective. So for metabolic cost, we could find these optimal settings using a brute force mapping method or some sort of automated optimization algorithm where we iteratively identify optimal settings. And these methods have been shown to work quite well to optimize for a predefined, measurable physiological objective, something like metabolic cost. But in reality, predefining an objective for exoskeletons can be a challenge. Really, when we consider the ways that individuals may use exoskeletons in their jobs or in their daily lives, it's likely that users prioritize many different objectives simultaneously, things like balance or effort or comfort. Individually, each of these things might be difficult to quantify, but one way that we've started to think about capturing them is to ask users about their preference. So we hypothesize that user preference likely encodes more than one of these physiological objectives simultaneously, and may include some of these less quantifiable and more subjective metrics. So before we can use preference as an objective for tuning exoskeleton controllers, we need to understand user preference and also how to measure it. And for the purposes of this study, we're simply defining preference by asking subjects what they like. So in the study that I'm presenting today, we hope to determine if exoskeleton users have distinct preferences, and if they do, can they repeatably identify these preferred settings in multiple dimensions, in this case 2? Do subjects prefer the same settings as each other? And then finally, what are the settings that they actually prefer? So far, we have conducted a pilot study with just two able-bodied individuals. And these people came in and self-tuned their exoskeleton control parameters in 2 dimensions in order to find their preference. In this study, subjects wore bilateral Defy ankle exoskeletons, which are pictured on the left. And then the controller that these exoskeletons used produced push-off torque as a function of the gait cycle and was based on the math from the Zhao science paper. So this particular torque profile that we used was parameterized by 2 parameters, the timing and magnitude of the peak torque. To find subjects' preferred parameters, we asked them to self-tune their controller. And to do this, they use a touchscreen tablet interface, which is pictured on the left there, that's mounted to the treadmill. The axes of this grid corresponded to the peak torque timing and magnitude, and touching the screen would instantaneously change the torque profile that the user experienced. These axes were hidden from the subject. You can see the interface that they saw is there on the left. And the axes were also randomized between trials. And we did this in order to make an effort so that the subjects couldn't learn the mapping between various trials. So depicted here is a representative trial from one of the subjects as they self-tuned. So for a given trial, we asked subjects simply to explore the space, try and sample settings from the entire grid. We asked them to walk for about 3 to 5 steps before changing the parameter. And then their only other instruction was to inform us when they found the settings that they preferred. So this was completely completely a free exploration. So we repeated this procedure about 4 to 5 times each time they started from a random initial condition. And then we also repeated this at 3 speeds, which I will not be talking about today for the sake of time, but happy to talk about it offline. So in this pilot study, both subjects were able to reliably and repeatably identify their preferred settings. So in this figure, the timing parameter is on the x-axis and the magnitude parameter is on the y. The crosses are the individual trials, the star is the mean, and the different colors represent different speeds. Now, the main thing that we noticed here was that each subject seemed to prefer a quadrant of the parameter space, but notably, they did not prefer the same quadrant as each other. We've also represented this just for visualization as the corresponding torque profiles for their preferred settings, where the black dashed line corresponds to the approximate bounds of the entire parameter space. And again, we see that subjects were quite consistent in their preferences. We quantified this precision in each of the parameters using a coefficient of variation. And in this case, a lower CV indicates higher repeatability across trials. So in this figure, you see that the torque timing is on the left and the magnitude parameter on the right. The colored circles represent individual subjects and speeds. And the black squares and error bars are the mean and standard deviation across all speeds and subjects. So the black squares are what I want to draw your attention to. And the main thing that I want to take away from this figure is that subjects were more precise in identifying their preferred torque timing across trials than they were in identifying their preferred torque magnitude. And the CVs are 1.3% and about 7%. So before the pandemic, we were underway with a full experimental study, including testing more subjects, analyzing the effective speeds, and that sort of thing. And as soon as this is over, we will be able to finish up that full study. But until then, it's just me testing on myself in my garage. So I'd like to take any questions. Thank you.
Hey, thanks, Kim. Do we have any questions? I have a question about test retest. I wonder if subjects are learning that touch panel. So did you mix up the the axes so that that they might do the same test, but have different locations on the test on the touch panel?
Yes, that was a key part of our experimental design. I didn't really have time to go into it, but the axes in between trials, the axes either flipped or flipped their orientation. And so a different, the Cartesian XY corresponded to a different magnitude and timing for each trial for that exact reason, that they weren't able to learn a location on the grid and say, oh, this was my preference last time, so I'm just going to go back there. That's not to say that they weren't becoming familiar with the process of using, maybe I perturb in this direction or the other direction. That's something that we're analyzing with the full study, is how people are learning how to use this and randomizing the speeds and conditions to account for that as well.
Great. Okay, I think we had Andy, Matt, and Michael, and let's see if we can squeeze them all in.
Okay,
Andy?
I don't know if we're going to hear from Steve Collins or his people in Stanford, but just in terms of philosophy or results, how is what you're doing comparing to what they're doing? Just superficially from a distance, it feels like very much the same. And so what's the relationship of the projects or the results?
Are you referring to the human in loop optimization work, or?
Yes, yes.
Okay. Yeah, I think that it's supplemental. I think that, I tried to point out early on that the human in the loop optimization work has shown some really cool results in terms of automatically optimizing for metabolic cost. We know there's a lot of challenges with using metabolic cost outside of the lab. So I think that, what we're trying to do and what Elliot's group at Neurobionics is trying to do is just provide an alternative method, something that may be supplemental. Different situations may call for different types of controllers. Different environments may call for different cost functions, and that preference, we want to make a robust method in order to use preference as an optimizing function.
So is it difference that, so you're using preference and they're using energy? Is that the big difference?
Superficially, that is a difference, yes. And it's not to say that metabolic cost is terrible and has none of its applications, nor is it to say the same about preference. I think that the idea is that it's a different way of thinking about it.
No, I was just wondering, I'm not trying to, not good or bad. I was just wondering what the difference is.
Yeah.
Okay, Matt?
So for your study, you're working with just the two parameters, the peak time and peak amount for that push off. But there's kind of also relating it to previous studies where you can also have like torque onset or when it ends. You can increase your parameter space quite a bit. Do you have any ideas or strategies that you can think of for increasing the number of parameters you're looking at? Since if you have two parameters, you have a nice grid, but what happens when you have 3 or 4? And will people be able to express a meaningful preference once you start increasing the number of parameters?
Yeah, I think that is a really important point. We've thought a little bit about expanding to multi-dimensional space, and also in collaboration with Bobby Gregg and their lower limb exoskeleton that has lots of different parameters. And so we're exploring, looking at some different mathematical techniques to reduce the parameters into a plane search around that. But I think that something that we're really interested in is does this type of method expand to higher dimensions? And really this study, I think we wanted to look at a proof of concept even for 2 dimensions. There's been some cool studies from Max Shepard, and Josh Caputo did a lot of the fundamental work on the emulator about tuning preference in 1 dimension. And so this was kind of the first step even to expanding it to 2 and see if people can encode their preference and find it on a 2-degree map. But I think that it's absolutely a question, and something that would be cool to study is people's ability to find their preferences in those higher dimensions, because it's absolutely going to be necessary.
Very cool, thank you.
Okay, Michael.
Thank you for your talk. One question that I had, so you said that the participants would take anywhere from like 3 to 5 steps before they basically tune to the next parameters. Do you believe that 3 to 5 step period was enough for them to really get a good feel, or that if you maybe let them go for a little bit longer, just kind of like when you're trying out new shoes or something like that, that they could even tune with higher precision in doing this?
Yeah, I think I just want to clarify that the minimum that we asked them to take was 3 to 5 steps. I wanted to avoid them just popcorning around 1 step at a time, but they were free to take as many steps as they wanted. And so I think to some degree, people were able to, if they wanted to take more to get a better feel for it, they certainly were welcome to. On average, it took people about 3 to 6 minutes to find their preferred setting, to say, this is the one I want. So break that up into however many times that they, tried a different setting. But at this point, that was totally up to them. And because we wanted to see what people would do with just a free exploration. Now, to answer the other part of your question, I absolutely think that this is a quantity that may change with time. Something like adaptation, like the shoes is a great example. And so I think that that's something that we're absolutely thinking about for the future study is adaptation and how does this change over time.
Thank you.
Mm-hmm.
Okay, thank you, Kim.
Thanks, everybody.
Let's move on to our next presentation. Next, we have Romeo Orsolino from Oxford Robotics Institute. And the talk is called Interactive Nonlinear Trajectory Reoptimization for Walking Robots.
Hello, Art. Can you hear me?
Yes, we can.
Great. So, introduction. So today, guys, I'm going to put two projects that are going to be presented at ICA this year that I worked on. Feasibility and the reliability of motion plans obtained with offline nonlinear trajectory optimization in such a way that they can be successfully executed on hardware robots. So both of these approaches a library Tower, published by Winkler 2 years ago, that many of you might be familiar with. This library allows us to transcribe a locomotion problem into a direct collocation, which can then be efficiently solved with a third-party solver.
Romeo, I think we might have lost your audio feed.
In the case of quadrupeds. So despite being a minimal parameterization, this is still simulations of different gaits on arbitrary terrains. The limitation are mainly an overall lack of robustness due to the
Romeo, I think we are getting a bad feed from you.
Romeo, can you try turning off your video upload, and then maybe that will help on bandwidth?
Okay, I'm assuming that Romeo is just reconnecting. While he's reconnecting, Aaron and Michael, do you have any instructions for how to get through the cafeteria quickly to have a fast lunch?
Yeah, so we're in typical style, we're running a little late, but we'll start the next session on time. And so we'll just shave 10 minutes off of the break. And yeah, looks like Romeo is back here. Romeo, can you turn off your video stream maybe and just share audio and the shared screen?
If he gets there, maybe ask him to run the clock backwards a minute or so.
Romeo, can you hear us? All right, so why don't we do this? Why don't we try and pick Romeo's talk up in a later session? And maybe if he disconnects and lets the internet clear out, everything will work better next time. So yeah, so I'm gonna turn off the YouTube live stream here in a moment. So for the poster break, again, you've got plenty of options. If it's lunchtime where you are, get lunch. If it's dinner time where you are, get dinner. Wherever you are, get some coffee. We've got a lot more to cover. And then head to the spatial chat rooms, head to Slack, or you can hang out in Zoom and see people here. All right, so we'll pick back up at 1 p.m. Eastern, so in about 1 hour.
John, I'm going to slide over to the right and talk to Anne about the talks this morning. You're welcome to join us.
Oh yes, also there's been a great discussion in the Zoom chat. I encourage people to go over in Slack to the speaker session 1 channel, or in the spatial chat room 9 to try and catch the first set of speakers there.
Just so you know, the one thing with the Zoom chat, right, is if you disconnect and reconnect, you might lose the whole chat history. So Slack will preserve that for you if you want to have that conversation there.
All right, great. I'll see everyone in an hour.